Okay, we're good. Welcome back to April 2020. Lesson videos, here we go. We had a quiz yesterday, so that means no daily quiz today because we didn't have a lesson yesterday. We're going to jump straight into it. Open up packets, 2-6, function families. This is pretty big deal, like big kahuna big deal. We're going to use this stuff for the rest of the semester. You're going to use it again if you come up into pre-calc or college algebra. It's that important. Like, function families is to algebra 2 and beyond what y equals mx plus b was to algebra half and algebra 1. So, pretty big deal. We start with a little bit of definitions. I'm going to have to keep heading over here to the other screen. You can all see. There we go. Wow. We have parent functions. Parent functions are the easiest a function can get. So here's what I mean. Like, you know about linear functions. Well, the easiest it can get is y equals x. That is the bare bones. You know about quadratics. Y equals x squared. You know about square root. This is all stuff from algebra 1. You learned about rational functions. And you notice that in every one of these instances, it's just the thing, just the thing, just the thing, just the thing. There's nothing else with it. That's why it's called the parent function. It's the big mama bear, the genetic template that everything else comes from. A transformation is what this is all about. I transform this by saying y equals 2x plus 3. Okay, now the parent has been transformed. I had a vertical stretch by a factor of 2. My graph for this thing used to look like this. Now I took this whole thing and I moved it up. Here's my vertical translation, up 3. So every part on here goes up 3. Every bit of it, the whole thing. So now you're at this. So the whole thing moves up 3, and then, because of this vertical stretch here, this point, instead of going over 1, up 1, it's going to go over 1, up 2. This is going to be twice as tall. This is going to be twice as tall. And you get this change in the slope. So it moves up, and it stretches. It has been transformed. That's what a transformation is. It's an alteration of the original parent function. Okay, translations, those are the easiest ones, and those are what you slaw? Ew, coleslaw's nasty. Those are what you saw in Algebra 1 and Geometry. Do you remember something like, take this triangle and move it so many units to the right, so many units up, and now it's here? Maybe you called it a slide. I hope not. Its official word is translation. A translation is when I move something left or right, up or down. That's it. Left, right, up, down. So this little table here is a bunch of different types of transformations. Now, the book wants to introduce these a piece at a time. I'm just going to go for the throat and give you the big part of this before we do anything else. And then we'll just keep talking about them as we run across them. Yes, this is just an old garage shirt. So, down in this corner of your notes, okay, right down here, I want you to write what I'm about to write. Okay, y equals of, do I got enough room? Yep. There we go. So first, a times f of x. A is for vertical reflections, also called reflect in the x-axis. That's when you take something and literally flop it over the x-axis, a reflection. Okay? A is kind of multi-purpose. If A is, I should say the absolute value of A, because whether it's positive or negative, that's a reflection. The value of it, if it's less than 1, it's a vertical compression. So, for example, if A was a half, think of whatever function you have is half as tall. You know, Hagrid sat on your cake. If A is greater than 1, that's a vertical stretch. Think y equals 2x. It's now twice as tall as it used to be. Okay. One that we do not see very often in Algebra 2, but we need to cover it because it's going to pop up every now and then, and you'll definitely see it if you move up, is B. B is grouped in the parentheses. And we're going to find out that in these parentheses or in the absolute value brackets or in the square root sign, in that grouping with x, we call this bass-ackwards land. Everything in here is going to have an opposite effect. And we'll get to it with the translations. But B is basically all this same stuff, but it's all for horizontal. And everything is flip-flopped. So here's what I mean. You're going to have, don't want to cover up my own stuff. Well, you know what? This is trash anyway. You're going to have horizontal reflection. And just like this reflected in the x-axis, this can be reflected in y-axis. Additionally, these said if A is smaller than 1, it's a vertical compression. So this says if B is, absolute value of B, is less than 1, it's a vertical stretch. If A was greater than 1, it was a, I said vertical. I'm tired, it's late, okay, horizontal, sorry. If A was greater than 1, it was a vertical stretch, so flip-flop. If B is greater than 1, it's a horizontal compression. And both of these are by 1 over B. They're always by the reciprocal. I know this is a lot to take in at the beginning. It's a lot of front loading. We get the front loading out of the way, we're just going to keep coming back to this. Okay? In fact, I might just screenshot this part so I can keep bringing it up. Okay. Next up, we have, do I have blue? I don't have blue. Well, I got a blue, but it's like a fine liner. We'll see. H is my horizontal translation. A horizontal translation means a slide from left to right or right to left. But because it's grouped in with the x, everything is going to be bass-ackwards. So I want you to draw this little line here with the plus minus on their opposite sides. Okay, we'll get to it with the examples, but this one's really easy to do. You just got to remember it's bass-ackwards land. And then finally, out here is going to be K. K is going to be my, what do we call it, my vertical translation. And it is regular land because it's not grouped in with my x's and y's, or my x's. And that is a slide up or down. Okay, this thing, this is like the holy grail of Algebra 2. We're going to come back to this thing in chapters 2, 4, 5, 6, 7, we're going to do rational functions. So chapters 8 or 9, I forget which it is. We're going to keep coming back to this thing, okay? Pretty important. So please have written down, like, put it in a place of honor in your notes, because we're going to keep coming back to it. Make it all pretty color-coded, whatever, because it's going to keep coming back and keep coming back and keep coming back. All right? If you need to pause it, do it. Otherwise, I'm going to erase this and move on to the examples of why this matters. Okay, so poke that thing. Okay, if you look over here, that's all that this says. It's the same stuff. You see how they have plus k or minus k? Up, down. Minus h plus h, right, left. Stretches and compression, greater than 1, less than 1. Okay, it's all there. So here is what a translation looks like. Oh, move that out of the way. If I have any graph, now the one all the way over there is it's called a sine wave, sine graph. And it takes that entire spaghetti noodle, and if I say plus k, I literally take the entire function and move it up k, or down k, all right? But you notice that it's outside, right here, this x grouping. If it's inside the x grouping, like here, it does the opposite thing. So think about it this way. If I'm making, say I'm saving $100 a week. I want to go buy myself a car, buy a new car. I'm putting, working at McDonald's, pressing that microwave button, and $100 a week is going into savings for your car fund. What if I wanted to buy something that cost $2,000? How long would it take you? Well, 2,000 divided by 100 is 20 weeks. But what happens, so now I'm going to say y is $100 per week. Well, what happens when along the way you crush your phone and you have to help chip in for a replacement phone? It costs you $300. Do you get to this sooner or later if you have to pay that extra $300? If your amount goes down by $300, right? Now all of a sudden, $100 a week, well, whatever weeks it was, I'm going to have to take away 3, right? Because it's going to take 3 more weeks to get there. So now it's going to take me 23 weeks, because $300, 3 weeks, is just, down the crapper because I broke my phone. This, because it's in bass-ackwards land, if I was looking at that on a graph, it would take this graph and it would shove the whole thing to the right 3 units, because it's going to take 3 more weeks to get where you're going. So it has an opposite effect. Just like, let's say instead, in the middle of there, you got a very generous grandma, and she gives you $300 for a birthday. Well, now you're going to get here faster. Now it takes 17 weeks to get there. So I'm going to add 3 weeks of value onto what it would have been. You notice now, if it took me this long to get this much money, I'm going to move that back. So now it's only going to take me this long to get there. This is why I call it bass-backwards land. It's just easier to remember. But everything that's grouped with X has an opposite effect on the graph. So over here, if I have plus or minus outside the grouping, it does what it says. It goes up or down. If I have plus 5 inside, then it actually goes left 5. Wait. Gotta make sure. Because the camera is reversed of what I see on there, and I always have to do. Okay. It's exhausting being a teacher. Okay. So left 5. If it says minus 5 on the other hand, then we're going to go right 5, which is why I wanted that. Y is A times F of. The B doesn't happen very often. Most of the time you're going to see it like this. Right next to this, I wanted you to say H is plus then minus, bass-backwards land. And K is regular land, like this. Okay? So, in we go. And I'm just assuming that anywhere along the way here, you're pausing where you need to. Okay, so over here, make bigger. Close enough, right? Close enough, yeah. Okay, they're going to ask how these two are related. They want us to do a table that's really overkill, where I have x, I have x minus 2, okay, and then x minus 2. Okay, so my y is my x. My y is x minus 2. If I were to go old school on these, remember making tables like this, -3, -2, -1, 0, 1, 2, 3. In my original equation, I plug in -3, -2, -1, da, 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 and I get those exact same things, -3, -2, -1, 0, 1, 2, and 3. If I take that function and I literally shift it down 2, I'm taking another 2 away from each of these outputs. So now it's at -5, -4, -3, -2, -1, 0, 1. Okay, so they want us to make a table. I think it's overkill. Wow, you can't even see that orange on there. Okay, we need to get rid of orange. Orange goes away. We'll use pink. Okay. They want us to do that. I think that's overkill. If it ever says make a table, don't. Just plug it in your calculator and look at the table that way. More importantly, what I can just say is, here's a graph. Okay, naturally I can't do that graph. I just got to wing it over here. So make a really butt ugly graph. Okay, so you have original graph. Start at 0, up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. Okay, down 1 over 1, down 1 over 1, down 1 over 1. You have original graph. X minus 2, yeah, I know it starts at -2 because we know slope-intercept form. But what I'm saying is you literally take this point and you move it down 2. You take this point and you move it down 2. Take this point and move it down 2. Okay? So you can do this for any graph. Now lines we already know, that's why we're using it to show you. But I could take just the nastiest looking graphs ever. Maybe it's been a while since you've seen something like this. But I could plot it by table, right? Put it in y equals, second table. Cool, plot points. I can take this thing now, and if I said move it down 2, you could literally take this point and just move it down 2. Take this point, move it down 2. Take this point, move it down 2. Okay, take the whole thing and move their points down 2. That's why they said do a table. But we can just let the calculator do the work for us. I'll move my melon over here. There we go. Okay. The way we could show that on a graphing calculator is if I had x, okay, and then graph it, see how much faster this is than Frank. Okay, there's my regular line. So if I took the exact same thing and I said x minus 2, you see that you actually see point by point it moves down 2. If I go to my table, oh, I want this back in auto mode. Okay, there we go. I can literally see 1 and 2, y equals x versus y equals x minus 2. All of them are 2 lower. So way faster if you just do it on the calculator. Now they're going to ask, what does this look like translated 5 units up? So, it's a parabola. It's been a long time since I've seen parabolas. I have no idea how to do parabolas, but I got a calculator. Come over here, clear that out, come back up. And maybe I just type in x squared minus 1 because I forgot how to do parabolas. It's been a long time since Algebra 1. I can now go to my table, and you can graph by just plotting points. Okay? So I hope this is big enough that y'all can see. 1, 2, 3, 4, 5. Don't do this on your assignments. Use graph paper. I'm doing this because all I have at home is a whiteboard. Okay? So your original starts here, 1, 2, 3, 1, 2, 3, 5, way off road, 1, 1, 2, 3, 1, 1, 2, 3, 5, off road, and this is going to be really bad. Ugh, okay, close enough, right? So if I say take this thing and translate it up 5 units, okay, so whether you're using, which way? That way. Use those points from your calculator, or maybe you just remember how to graph these. Plot points, connect dots. Yay. Now take this same graph and move it up 5 units. Well, move -1 up 1, 2, 3, 4, 5. Take 0 and move it up 5. Take 0 and move it up 5. Take, what's that, 3 and move it up 5. And now those are off road, so it's like way up there. Okay. Oh, gotta shift you back over. Okay. So you take this self-same graph and you move it up 5 units by taking each one of the points that you plotted from before and move them all up 5. If I look at that in terms of a function, now they said what's the graph? But y equals x squared minus 1. If I want to move that up 5 units, well, this is the k spot. K does vertical translation up and down, so I will just add another 5 to the k spot, getting x squared plus 4. Now I can show this 2 different ways on a calculator. I can go down here, and remember when we did that whole storing using variables and all that? I can literally say not stat. I can say variables, the y's, the function y1. I can take the original equation and add 5 to it. Okay, so you get original and then add 5 to it. It goes up. Okay. Additionally, I could have taken that same thing and maybe I would, just to prove to you it's the same, x squared plus 4. So I'm taking 5 and adding it into the k spot. When I go to graph, you see, shoo, it just colors in the same thing. So that's how I know I did it right. But I would like you to do the same thing. All right? You're going to take that line and its companion and tell me how are they related. You don't even have to graph them. Part B. Okay, in this one you have to graph. They're going to say take y equals 3x. That'll be your parent. Move it up 2 units. I would ask you to do it. No, don't do that yet. I would ask you to do it by points. Don't just say, well, I'll start at 2 and do my regular line. Please pause, do both of them legitimately. Okay? And then I'll be here with some answers. Okay, so if I go from y equals 2x over to y equals 2x minus 3, I see that there's a negative 3 in the k spot. Remember, it goes back to this. Y equals a times f of x minus h plus k. If I see something in the outside spot here, it's not in parentheses with the x, then I know it's k. And since k does this business, I know that to get from here to here, and it's negative, I would use your big kid words. I'm going to call that a vertical translation down 3 units. Okay, that's how we officially say it. Part B says, what do I do with this graph if I translate it up 2 units? Well, I get my 1, 2, 3, 4, 5, 6. Okay, hopefully that's good enough. You have your original of start at 0, up 3 over 1, up 3 over 1, down 3, back 1, down 3, back 1. Okay. So there's my original graph. If I'm going to translate that up 2 units, make big, then I take each of these points. Okay, don't get lazy. Take this at 0, 0 and move it up to 0, 3. Take 1, 3 and move it to 1. Oh wait, no, we're going 2 units. Sorry. 0, 2. Take this 1, 3 and move it up to 1, 5. Take 2, 6 and move it up to 2, 8. Take each of these points and move them up 2. And there you go. Okay. I want you to get into the habit now, while everything is nice and easy, while we're dealing with linear functions, because pretty soon they're not going to be linear. In fact, Algebra 2 is kind of where you solidify your knowledge of nonlinear functions. So, next up, if you got questions, here's a page with more examples. Try them, use your mind, screenshot, show me what you did, send it to me and say, did I do it right? Otherwise, I'm just going to keep on rolling. Okay? Be honest with yourself. Okay, horizontal translations. Okay, I already talked about how... Oh, I gotta move that again. Move my melon back up here. Move this down here. Oh no, we'll put me right there. Yeah, yeah. Okay, good stuff. Graph shows projected altitude of an airplane. scheduled to depart airport at noon. Should probably not have my mouse clear on the other side of the thing here. Okay. All right. Can y'all see the mouse over here? Does it not show up on the screen? Oh no. Okay, I gotta change that setting. I'm not gonna do it now though. I just want to keep going or I'll lose my train of thought. So here's my time in hours after noon. Here's my altitude, and you notice that they say in 1,000 feet. They're telling you that because if I just had 3,915, well, that'd be a really low flying airplane. So if this shows time and height, do you understand why the plane is showing this particular graph? You take off, so you go way up. This little bank is usually them circling around, getting to the direction they're going to actually be going. Okay, now they're going to pop up, keep going up to cruising altitude, and they're going to cruise at that altitude for a while. And then you get to whatever airport you're going to go to, and they steadily descend to the airport. That little, right here, that little dip and then over, this is usually them, or no, it was the other way around. It was like, yeah, there you go. This is usually them, like, they get to the city and they whip around a little bit and then line up with the actual direction of the airstrip, and then they start coming down. But that's why the graph looks like this. It says it leaves 2 hours late. Do you see why the whole function moves to the right? Because I would have been at cruising altitude at this time, but because it's 2 hours late, it's not going to get to that cruising altitude until this time, which means there's the rest of the flight path, right? I'm not going to leave until 2 hours later. So if I'm late, if I'm taking away time, it moves it to the right. What function represents the transformation? Well, y is a times f of x minus h plus k, and they're starting with just plain old f of x, because clearly this isn't a linear function or anything like that. If I'm going to modify this function and I move 2 to the right, remember when we had you do this? If I'm going 2 to the right, then I'm going to minus 2. I will literally just have y equals f of x minus 2. 2 to the right, put a minus 2 in bass-backwards land, grouped in with the x. Okay? So, down below, it says, suppose the flight leaves 30 minutes early. Can you write it? So if we went that way for late, can you figure it out? Also pay attention, the original was in hours. This says it leaves 30 minutes early. And we're back. I had to pause, get a drink. Pretty simple. Y is f of x. If I'm going the other way, then I'll be adding something. Wow, you can barely even see. I need to stop using blue. Bad Sullivan. Y is f of x plus. Okay, I know it's going to be plus because I'm going the other way, because it's 30 minutes and the scale of this is in hours. Add a half. Okay, so I'm putting in how much time it would take me to get to a height, but I'm going to add to it because I'm going to get to wherever that was a half hour earlier. So if you would have landed here, you're going to land here instead a half hour earlier. So I moved the graph to the left. Left is plus bass-backwards land a half hour. And there you go. So move on to poke. Okay, again, same stuff. You're going to take this graph. Oh, that's right. It doesn't show it. Okay, you're going to take those graphs and use your calculator here. Okay, to make the table for the original points, and then take those points and move them left and right and all that kind of business. Okay, so like this one, I see a +1 in parentheses in bass-backwards land. So instead of saying +1 is right 1, bass-backwards, we'll go the other way. But we want to use our big kid words and say that's a horizontal translation left 1 unit. Or if you want to then say left 1 unit. I don't care. But we need to see these words, horizontal translation. Okay? All right. Again, if you want to just snap a picture of it, say, hey, did I do it right? Send it to me, I'll get you. Okay. Reflections. Remember, y is a times f of b x minus h plus k. So now we're talking about this dude right here. Remember, these are vertical. Oh, I forgot to screenshot. Crud. These are vertical reflections. Okay, vertical reflections take a graph wherever it would have been. So over, oh, see, I keep forgetting to move this. There we go. So take the down there, the black graph, and you would reflect it over the x-axis. I take this triangle and I flip it like this. Okay, reflected over the x-axis. That's a vertical reflection in the A spot. What B does is if there's ever a negative right here, that's going to take this triangle and it's going to flop it over here instead, over the y-axis. So we're going to say this is either a horizontal reflection, or I would say reflected in the reflected over the x-axis, reflected over the y-axis. Okay, so reflections, negatives. Notice right there. Okay, is the negative in with the x, or is it out in front of the whole works? That's how you tell the difference. So take this, reflect it in the y-axis. What's a function rule for it? So reflect in the y-axis, I was supposed to put a times f of b to the x minus h. I really should just leave that on here, huh? Okay, we said reflected in the y-axis means I'll put a negative in the b spot, meaning grouped with only the x. So here's the difference. If I take f of x is 3x plus 3, and I reflect that over the x-axis, then I will negate the entire honkin' thing, which means it's going to look like a negative in front of the whole honkin' thing, which is a negative 3x minus 3. See how everything negative, everything negative. Versus if I go to the y-axis, now it's f of a negative x. So I replace only the x with a negative x. Okay, you only negate this part versus the entire thing. That's a difference. X-axis, negate it all. Y-axis, just the x. Cool? I hope so. And then my answer will be g of x, because they did say my new version of it is negative 3x plus 3. Now, I still want to simplify it, but you notice that this one, it literally reflected, so it's down lower. It starts at the negative 3, whereas this, it's still going to start right here, but now instead of going this way, it's going to go this way. It literally reflected over the y-axis. So it's just about where you put your negatives. Oh, I accidentally did the got at 3. Oops. Okay, we'll find a different one for you. Yeah, right there. Go ahead and try that one. Okay, take this and reflect it over the y-axis. I hope you actually did that. Y is 3x, or sorry, f of x is, if I reflect in the y-axis, you just stick a negative right here. Now in this case, yeah, I don't edit my videos. It's still going to be a negative 3x regardless. Where it's going to change is if you got other stuff with it, like a plus 9, having the negative here versus out front, right? Completely different thing because whether it distributes or not. So just want to double check that. Next up is, right, we did those. There we go. Okay, now these, you notice right here, there we go. Okay, right here it says stretch and compress. Those are specific to stretching and compressing. Up here in this blank spot, we're going to write a dilation. Okay. A dilation can either be a stretch or it can be a compression. It can be either one. So dilation is the umbrella term for both of these. Okay. You notice the first one says, oh, if I moved it, a blank multiplies all the values by a factor greater than 1. Well, what's going to make things greater than 1? A stretch or a compression? Okay, and it goes back to y is a times f of b x minus h plus k. If this guy has a less than 1, it's a vertical compression. So values less than 1, like a third or 5/8. Okay, if that absolute value is greater than 1, like 6 or well, oh, how about 8/5? That's a vertical stretch. Okay, so those are vertical stretches and compressions. Now you can do it with horizontal as well. We don't see them as often, but I am going to write it because sometimes it shows up. Remember we said if absolute value of b is less than 1, this had a vertical compression. This will have a horizontal stretch. And it's always by the reciprocal of 1 over b. Flip-flop. If absolute value of b is greater than 1, well, here a greater than 1 was a vertical stretch. Here it's going to be a horizontal compression. Okay, because it's grouped in those parentheses. It's bass-ackwards land. So that's what all that gibberish says. You notice, there we go. You notice right up here, they took that sine wave, and if I put a 1 over a in front, a fraction smaller than 1, then it compressed. Someone sat on the wave. If they have an a like right here, if they have an a in front of it that's greater than 1, well, it's going to take that wave and stretch it out, make it 3 times bigger. So, they want us to do it by table again. I think you guys know how to just take numbers and multiply them by 3. If I see it in a graph, oh, there we go. Put me over here. There we go. Okay. If we have a graph, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So you take the original, it says -5, 1, 2, 3, 4, 5, 2. -2, 2. 0, -3. Okay. 3, 1. And 5, -2. So if the original looks like this, if I take and put a 3 in front of it, well, 3 is greater than 1, so it's a stretch. I'll take all of these y values and I'll stretch them out 3 times as tall. So instead of being at -5, 2, it'll be -5, 6. Instead of -2, 2, it'll be -2, 6. Instead of 0, -3, it'll be 0, -9. Instead of 3, 1, it's at 3, 3. Instead of 5, -2, it's 5, -6. And you can see it follows the same pattern, but it is literally stretched 3 times as tall. Okay? So, if you ever run across that, you literally just take those points, multiply them by whatever your scale factor is. So, oh, hey, look at that. Do the exact same thing, but 1/3. Pause it. Do that. Go. Again, I hope you did that. Pretty simple. I'm going to quick wing it here. You actually do it for real. You had your original. It looked like this, this, right? If I take all of those points times 1/3, instead of 2, it's 2/3. Instead of 2, it's 2/3. Instead of -3, it's -1. Instead of 1, it's 1/3. Instead of -2, it's -2/3. And I get, ooh, that was trash, literally 1/3. Someone squished it. Okay, sat on. Okay. Well, just like before, if you got questions, ooh, oh no, we're gonna do the okay, yeah. I like those. We're gonna do those ones. There we go. Make big. Okay, big. Writing the equations. Or is that what the next thing is? Oh, no, that's the next thing. Okay, vertical stretch or compression. If I see y equals x and they tell me vertical stretch by a factor of 4, here's the spot, the a spot in front of the variable. That tells me, well, if it's a stretch by 4, I'll just jam a 4 in there. If it's a 1/2, I'll jam a 1/2 in there. Now it's a compression. Okay, I was jumping the gun. I was thinking that it was this stuff. Okay, the last thing. The last thing is putting it all together. Move this down here. So, one more time. Y is a times f of x minus. You have a vertical stretch and compression, vertical reflection. B, not seen often in Algebra 2, horizontal stretch and compression, always by the reciprocal, and horizontal reflections. H, that's one we're going to see a lot. That's your horizontal translation, left and right. I'm going to try orange again. Can you see it? God, that's really bad. Did I have a blue? Come on. Why don't I have a blue? I found a blue. It's a big stinky though. And K. There we go. K is my vertical translation. So, this is your holy grail. You're going to keep coming back to it over and over and over. It's also on your holy sheets for the chapter, for the whole course. Here we go. It says the graph, g of x, is the graph f of x equals 4x. So I'm going to start with that. Original. Compressed vertically by a factor of a half and reflected in the y-axis. Well, a vertical compression is in the A spot. There's already a 4 in the A spot, so you just jam a 1/2 with it. Reflection in the y-axis. Go back to your notes. That's in the B spot, grouped with x. So I need a negative just with the x. And then you simplify it. You turn that whole honkin' works into g of x is negative 2x. Okay? I hope this is big enough for y'all, right? I hope so. Here, let's make that even bigger. We don't need to see the bottom problem yet. There you go. Okay, take it a step further. Part B. How do I go from f of x to g of x? So what was done? If f of x starts here, and g of x ends up here, what did we do? Well, my A spot went from a 2 to a 6. From here to here, I multiplied by 3. 3 is greater than 1. I have a number greater than 1 in the A spot. So I would call that a vertical stretch by a factor of 3, because that's what I multiplied by. I also had nothing out here in the K spot, and now I have a -1 there. So I go back to my notes, and the K spot is vertical translations, either up or down, positive, negative. Since it's a -1, I'll say that this had a vertical translation down 1 unit. There you go. Okay, you find out, how did I change this into this? So I'll move this out of the way and say, do the same thing down there, okay? That feels really weird. I'm trying to point down to a problem, but I'm actually like pointing at my belly button. It's kind of funny. Anyway, pause it, do the thing. Okay, so we're starting with f of x is x. I'm going to take that and stretch it vertically by a factor of 2. Well, this is my vertical stretch spot. So I'll just shove a 2 right there. And it says translated down 3 units. Well, that's the K spot. Again, no parentheses yet. So I'll put a -3 right there. G of x is 2x minus 3. Part B, how do I go from... Oh, I'm tired. Oh, boy. Okay. F of x is x squared to g of x is x plus 4 squared minus 2. So I noticed 2 things that happened. 1, there wasn't anything grouped with the x. Now there's a plus 4 grouped with the x. Go back to your notes. This is horizontal translation land. And it's always backwards, so because it's plus 4, I'm actually doing a horizontal translation left 4 units. There was nothing out here in the K spot. Now there's a -2, which is, go back to your notes, a vertical translation down 2, or use the arrow or whatever. Okay? So you keep coming back to that big holy grail thing, and you just match. So get rid of this one. And one last time, ladies and gents, all right, folks, I want you to do these regardless, just because this puts it all together in one spot. Pause, go. I hope you actually did that. So, if we start with f of x is 4x, and I'm going to translate it up 5 units. I go over to the K spot and I put plus 5. Nice and easy. Okay. The reflection in the x-axis. This is why I wanted to do this one. You're supposed to negate the entire thing, right? Not just the x, the entire thing. But that's going to change this plus 5, right? Because now if I distribute a negative, I end up with a -5. Well, that's down 5 units. They said to go up 5 units. But if I translate up 5 units and then I reflect, that is actually down. Which one is it? Okay. This goes back to geometry. You notice that this is multiplication and this is addition. Multiplication and addition are not commutative, order doesn't matter, with each other. So the order you say them in matters. If I translate up 5 units and then I reflect in the x-axis, then g of x is negative 4x minus 5. What that would look like is taking this line, moving it up 5, and then reflecting it over the x-axis like this. Versus if I had said reflect, then translate, now I would have negated the whole thing, but that's the only thing there, and then gone up 5. What that would look like instead, I just got to get rid of the whole thing, don't I? Is original, reflected, then up 5. You see how it ends up in a completely different spot because the order that I say them in. Because multiplication and addition are not commutative with each other, so the order I say them in matters. We're going to get to that again when we do composition of functions. Okay, you can actually save money in the real world by forcing people to do it a certain way when they ring up your bill. You know what? I want you to put a note next to this. When you write it, okay? When writing your transformations, always do reflections first. Okay? I want you to write that in your notes. Because it kind of boils down to the order of operations. If you're already looking at this, and then you have to turn this into words, if I take care of multiplication before addition, I have followed the order of operations. I will get to where this graph actually is. Okay? But if, like that one, it tells you an order, you have to follow the order. And the last one, if I have f of x is x over 2, and g of x is negative 2x plus 4, how did I get there? Well, first would be maybe I should write that as 1/2 x, make it look a little more familiar. So I turned a 1/2 into a negative 2. Well, 1/2 times what equals negative 2? Dividing by fractions is easy as pi. Flip the second and multiply. So I multiplied it by a negative 4. That's two different transformations. The first one is a vertical stretch by a factor of 4 because I multiplied by 4 and 4 is greater than 1. The second part is the negative. Don't say vertical stretch by negative 4. The negative is its own transformation. I'm going to say vertical reflection. Or you can say reflection in the x-axis. Both of those are correct. Okay. The book likes reflection in the x-axis. I like saying vertical reflection because this has to happen at the x-axis, so you have to do it first. But if I say vertical reflection, I can reflect about an origination point or a vertex. So, potato, potato. And there was nothing outside of this in the k-spot, but now there is a +4 in the k-spot. Again, I know it's k because it's not grouped with the x. And k is my vertical translation spot. In this case, because it's +4, up 4 units. Ta-da! So, an hour of video lesson. God, I hate these things. But hopefully you're able to just watch this, and the few times you had to pause and do a thing, hopefully it should still be the 90-minute class. So, assignments on Planbook. I'll also send it out on our Mind. Go get them.